What's up, guys? It's Misha. Have you ever experienced something like that? You're sitting, working on the circuit, then you turn on the switch and boom! Oh shoot! Yeah, that might happen with all of us. Sometimes due to the failed components or incorrect ratings, but sometimes due to the unforeseen transient. When you turn on the switch, the circuit moves from one equilibrium point to another, and sometimes it can cause some problems as you've seen before. However, if there is enough control in the circuit, the transient period can be avoided. Sounds too cool? Let's look at the example.
Say we have an RL circuit with zero initial conditions, and at time equals zero, we apply the sinusoidal voltage. So we had a steady state before t equals zero, and we will have a steady state after some time when we move the switch. In between of these two states, we want to know how our voltages and currents change. Specifically, in this example, we are looking for the current. I will do analysis using Laplace transformation, which is a very powerful method that allows me to avoid dealing with differential equations. And it can be used for more complex circuits, but the steps how you do the analysis, they're the same. Okay, let's start. The first step is to write all the known signals and parameters in S domain. As we have zero initial conditions, the equivalent model for the inductor in S domain does not have any voltage and current sources, so it will be just SL. The resistor will be R, and the sinusoidal voltage has the following Laplace transform. Then at the second step, we use KCL, KVL, Ohm's law, nodal analysis, mesh analysis, or whatever analysis you know to find the signal you need. In our case, we can just use Ohm's law, and the current equation looks like this. Then at the next step, we do inverse Laplace of the function you found to have the signal in time. And usually we don't take the integral, but we look at the table of the Laplace transform pairs for the standard functions. In our case, the function is not a standard, and we need to write it as a sum of the simplest fraction that have tabulated Laplace transform pairs. This method is known as a partial fraction expansion, and for our function, we have two fractions. The first one is, and the second. The first fraction, as you can guess, transforms into shifted sign function, and it represents a steady-state function. The second fraction transforms into exponential function. When t increases, this term decays and becomes zero after a long time. So this fraction represents transient. I will skip how to find the coefficients and just write what they are if you do calculations. Now, when we know the coefficients, we take inverse Laplace transform, and our function of current and time is the following. Phi in this function is an inverse tangent of omega L over R. The first term of the function is in simplified way, and the second term also can be simplified, but we need an exponential term in this form for analysis purposes. Coefficient in front of exponential function can be set to 0, so eliminating the exponential term at all. To do this, the numerator must be 0. That means that the tangent theta must be omega L over R. Summarizing, to avoid transients in the circuit, we should apply the sinusoidal voltage with a phase shift whose tangent is omega L over R, or turn on the switch at time that corresponds to this phase shift in time.
Now let's look at the example with some numbers. I have an RL circuit with such parameters, and let's see what I get when I turn on the switch at t equals 0. I have a high value of current during the initial phase of the transient due to the exponential term. This current increase may cause a problem if the circuit is not designed to tolerate a high current. Now, let's have a look at the waveform when I turn on the switch at time that corresponds to voltage phase shift of 86.19 degrees. In this case, there is no such a high current and transient itself, because in this case the exponential term is 0. The system enters steady state right after the switch is closed.
Hey, that was useful and pretty interesting. Could you imagine before that choosing appropriate time of switching may have such an impact on circuit behavior? This idea is used in vector control of motors and software simulation when you want to start circuit simulation from steady state. Besides, we went through the process of transient analysis step by step, and now you can do analysis of any other circuits. Test yourself with the circuit I'll give you at the end. If you like this video, hit the like button, share it with your friends, and subscribe to my channel. It was Misha, thanks for being in my class today, bye!